In this video, we're going to be covering conservative vector fields, how to determine whether or not a vector field is conservative, and if it is conservative, how to find the potential function for that vector field. Now, we're going to look at the vector field where our first component, which we'll call little f, is equal to 2x plus 5y, and our second component, which we'll call little g, is 5x minus 3y. Now, to verify that this vector field is conservative, the following condition must be met, where we have the partial of f with respect to y must be equal to the partial of g with respect to x. Now, why is this the case? We're going to go ahead and assume that we have a conservative vector field here. And in this case, it is true, because if we take the partial of this with respect to y, we get 5, because this 2x is treated as a constant, it disappears. And we also have a similar thing going on with the partial of g with respect to x. We just have this 5 here. So these are indeed equal, and we know that we have a conservative vector field. So the condition is checked. Now, a conservative vector field is a vector field that is the gradient of some potential function. And if you recall, the gradient of some function, which we'll call phi in this case, is equal to the vector where the first component is the partial of this function with respect to x, and the second component is the partial of this function with respect to y. So keeping this in mind, if f is the gradient of this potential function, then we have that the x component, or the first component here, is equal to f. So the partial of phi with respect to x is equal to our f component up here, and the partial of phi with respect to y is equal to the g component. And if we take the partial with respect to y of this, which is what we've done with f, and the partial of this with respect to x, which is what we've done with g, then we have, sorry, that's kind of bad notation, but we know that these must be equal, because if you recall about second partial derivatives, even if you switch the variables here, these will always be equal. So that's why when we check if f partial y is equal to g partial x, we know that f is the gradient of some potential function. So now that we've verified this and kind of reasoned through why it is actually true, we're going to go ahead and show how to find the potential function knowing that we have a conservative vector field. So we're going to go ahead and start off with something that we know. We know that phi with respect to x, our potential function with respect to x, is equal to this first component f. So we can write it out like so. Phi with respect to x is equal to 2x plus 5y. And we can integrate both sides of this equation. If we integrate both sides of this equation with respect to x, then we just get the phi back, because it's a partial derivative with respect to x. Integrated with respect to x, we just get phi back. And then we have here x squared plus 5yx plus some constant c. But there's something a little bit special about this c, because this c could depend on y. That is, if this value were, say, 4y, and we take the derivative with respect to x, this is treated as a constant and disappears. And since we're integrating with respect to x, this could be a function of y. So that's why we denote it like this. So we're a little closer to determining what our potential function actually is. We have these first two terms here, and then we have some constant. We just have to figure out what this constant is to actually get our full potential function. I'm going to erase some of this up here just to free up a little more space. But what we're going to do next is we are going to take the derivative of this function with respect to y, partial derivatives. And we will get that the x squared disappears, but we have 5x plus some constant with respect to y, where we have c prime y is just the derivative of this constant, right? But we know that the partial of phi with respect to y is equal to our g component. So we can actually set this, or sub this out with this g component here. We have 5x minus 3y equals 5x plus this constant where we have taken the derivative. Now, these 5x's will cancel, and this makes sense because if this is something that depends on y, we can't have x's in the equation. And then to find this, we can integrate both sides, where we have this just goes to some constant, while this here goes to 3 halves y squared is equal to our constant with respect to y. But now we can plug this back in here, and we have that our whole potential function is equal to x squared plus 5yx plus or minus 3 halves y. Oh, and I should add plus some constant, right? Because we're integrating. Tap on that plus c at the end. And this is how we find the potential function given a conservative vector field, and how to check in the first place if it is conservative. So this pretty much sums it all up, and yeah,